So where we are with this project is we have a rotating base that we're going to put a structure up on top, similar to this robotic arm that we have. And we need to determine what the torque is required to be able to rotate this. So in other words, we have a mass sitting here, it's sitting down on this plate, and we're trying to determine the amount of friction that we're going to have to overcome with our motor to make it rotate. So to move forward, what we're going to do is I'm going to build a representative sample of that rotating base. So this is the part right here up on top is what everything's going to sit on. This mass represents the structure that's going on top of that. And that's an assumptive. So I'm thinking, it's about 5 pounds is what we're doing. And this base underneath is going to be what's supporting it up. We're going to have the mindset that it's not going to be tilted, and also not all the weight is going to be on that shaft of the motor, because that's not good for it. So to determine the frictional force, what we're going to do is I'm going to set up my camera, and or I have somebody measure the edge right here so I can get the height that we go up to. But in this situation, I want to be able to be distance from somebody. And so I'm going to have my webcam set up. The height right here is the same height as these reams of paper here. And I'm going to lift up this angle until it starts to be able to rotate. There we go. And so once I sort of know where that's at, I'm going to go through. I'm going to click on my camera, set to 5 seconds. And we're going to click go. We're going to let it take a picture. All right. I'm probably going to do that 3 or 4 times because I feel like that's not a precise location. Right there. All right, so let's take a picture again. Okay. Then, with that in place, what we're going to do is we're going to take that in. We're going to determine what the size of that triangle is, so what our angle is, and be able to make some decisions about that with our friction. All right, so my next step, I'm going to use PowerPoint because I know that's readily available to everybody, and we'll make our next couple decisions with it. And so I'm going to go in. I've got my image inserted already. I want to insert some shapes, which are just going to be lines. So I'm going to go down here to where it intersects the material, right? I'm going to add another line now, and I'm going to intersect with that origin. I'm going to go out to the middle of the material. So I want it just as much on this side as I do on that side. I'm going to now zoom in a little bit. I'm going to grab a protractor off of the internet. Now, if I was doing this in more of a research type of structure, I probably would have went for this centimeters distance right there. That's going to be a little easier to get a little bit more accurate. I also probably would have done this through Photoshop or pulling it directly into CAD software to where I could get a true accurate angle. So I've got this. I went in, I removed the background on this so I can sort of see, and I can set this right up on top of my origin. All right, let's see. There we go. And now I've got my angle. I'm going to go in, check to make sure it's in the right spot. It looks like that's actually a little high, so I'm going to go there. And I'm looking at an angle that's right around 31. So now I can back out. I have that my mass is 2.75 kilograms, which is 2,750 grams. I now know that my angle is 31. I've got my my distance to the center. So what I did was I took the center where this motor would have been mounted, measured the distance out. I got 15 centimeters there, took it in half, so I got 7.5 for my average distance. I'm now calculating my frictional force, which is going to be the mass of my weight, which is the 2,750 times the sine of my angle, which is 31. And to determine the torque, I'm going to take that and multiply it by 7.5 grams, and we'll get our torque, which I've got my calculator right here. So I'm going to pull it up. So I've got 2,750 times sine 31 equals 1,416 times 7.5. And right there, what I get is I get a torque of 10,622.7 grams centimeters, which is a lot higher than most of the motors I've been working with. So let's do that test again. What I've done is I've added some spacers right here. That's going to hopefully reduce the friction for me to where when I angle it up, I'm going to have a lower angle and be able to calculate the torque in that way. Again, I'm looking for either the angle here or the height right there, because if I have the height, I can calculate the sine over there, which is great, or the angle over there. So I'm going to do the same thing. I'm going to click on my camera. I'm going to lift up, try to figure out what much earlier. Right there. All right, let's do it again. Right there. Good deal. Let's do it one more time. All right, cool. And now we're going to take that in and we're going to start working with it to determine our friction. So I've gone through and I've already done the measurement here, and I've got my mass, which is the same, which is 2,750. My angle is now 21 because it broke a little earlier. My distance is now 7 because I spaced those discs a little bit closer. And when I calculate for my torque, I've got my 2,750 times sine 21 times 7 centimeters. I get significantly a lower number here of 6,898, but this is still well above the torque range of the motors that I'm using. And so let's look at other ways that we can sort of increase our torque with using the same motor. So my first thought here is I shouldn't be making this out of 3/4 inch MDF that is this distance wide. But in this situation, what I'm going to do is I'm going to move my stepper motor out from under the disc, and then I'm going to add a gear to it. So we're going to imagine there's teeth all along the edge here, there's teeth all along the edge here. And when this begins rotating, this of course is going to rotate slower. And what we'll see in a moment is that torque and speed are the opposite of each other. And so if I can make this rotate really slowly, I can use a small amount of torque and get a lot out of it because we're sort of doing that trade-off with speed for our torque. So to do that, we're going to develop a smaller gear to go on top of our motor and then add gear teeth to the outside of the larger disc. We're going to consider the smaller one to be our driving gear because that's what's connected to our motor. And the larger one that I've got here in orange is our driven gear. The calculation that we can use is angular velocity of 1 over angular velocity of 2, number of teeth 1 over number of teeth 2, diameter 2 over diameter 1, and torque 2 over torque 1. And we do see that the angular velocity and the torque are inverted. And so we do know that when we increase our speed through gear ratio, we're losing our torque. And so what we're trying to do, though, is we're trying to actually increase our torque. So this is going to move very slow, which is a reason also that in my mind we're going to use a stepper motor because we're going to have it revolve multiple times. So I'm going to plug in my known. So I know that T1 is 900 grams centimeters. I don't know diameter 2, so that's what we're looking for here. I then know that my driven gear, I'm going to have 6,898.5 grams centimeters for my torque. And I know that my diameter is 15 centimeters. And so I plug that into the calculation. I then solve for D1, and I will be able to know that if I put a gear up here that's effectively connected and we keep the same amount of friction on the bottom, I should be able to move it with a gear that is right around 2 centimeters in diameter.